I am going to present a particular aspect of the project I am dealing with. Right now, I am trying to examine the particle trapping ability of auxetically treated foam. A significant aspect of this is the particle loading ability of auxetic materials. As a quick review, auxetic materials are negative Poisson's free issue materials. That is, the way they behave when a stress is applied, tension or compression, is converse to what is observed in conventional materials. That is, while normal materials compress in the transverse direction when tensile load is applied to the material actually expands more. The inverse is true for compressions. This is thought to be due to the buckling of material's cell ribs upon a prior compression stage, which, when tensile loads are applied, gives a huge volumetric increase, allowing the material to expand both transverse and axially. In a journal published in Molecular Simulation Journal of Experimental Nanoscience entitled Modeling the Mechanical and Mass Transport Properties of Auxetic Molecular Sieves, an Idealized Organic Polymeric Honeycomb Host Guest System, Alderson and Company tried to simulate the loading of buckyballs C60 and C70 into a polymeric array which is composed of acetylene molecules linked by benzene rings. The aim is to simulate the structure of conventional honeycomb structures in the molecular level. For the sake of naming convention, the researchers named the structures NM-flexene, where N and M are the number of acetylene links in the diagonal and vertical directions respectively. They used Re-flexene for the auxetic structures. When the structures are deformed in a way as to how conventional honeycomb structures are deformed to transform them to auxetic honeycomb structures, the negative Poisson's ratios of the transformed NM reflexene structures were verified. In particular, in their study, they focused more on 2,8 reflexene since the size of the pores are similar enough to C60 and C70 molecules to be used for loading. Using a Silicon Graphics O2 workstation running the Sirius molecular modeling software, riding force field simulations were done to observe the effect of forcing C60 and C70 molecules into the pores of the polymeric structure. Conditions are made sure that interactions between atoms are minimized and that deflections or attractions are nullified. The loading of the molecules are done using a Monte Carlo simulation, with which number of hits are counted against the total number of atoms that were produced for the duration of the simulation. Plots of the percentage of hits were then plotted against the stress experienced by the material. What they found out is that the loading of the molecules into the structure increased as the stress increased. At some point, the loading will peak before the loading percentage drops down drastically. This is attributed to when the auxetic structures lose their auxetic property. From this, they were able to conclude that as stress increases, pore sizes increased, leading to a higher loading frequency, and therefore, the entrapment and release mechanism for an auxetic network is stress or strain dependent. This study is relevant in applications that require the controlled release of components into a system. What comes to mind are applications involving the release of drugs into the bloodstream. Current topics of study involve methods that include the encapsulation of drug molecules into nanocapsules composed of layers of polymeric compounds. These methods take into account chemical interactions between the system and the nanocapsules, as well as the nanocapsules and the drug molecules to work. But issues such as biocompatibility and toxicity remain, especially in the fabrication of such molecules. The method as described by the authors would only depend on the stress and strain levels of the auxetic networks to work, and as such, may be a viable alternative to current nanocapsule technologies. However, as can be inferred from the structure of the guest system showed earlier, the auxetic network as studied by the authors of the study aren't particularly easy to synthesize because of the degree of order of the polymeric molecules involved. However, foam, despite the randomness of the unit cells, can easily become a template for 3D auxetic guest systems. Foam unit cells can be idealized as tetrahedron in shape. Auxetic foam cells, therefore, can be idealized as shrunken tetrahedron cells, and it can be shown that under some mode of deformation, the cross-section of a unit cell shows a degree of similarity to conventional auxetic honeycomb structures. Deformation under this model are visible in some of the unit cells of actual transformed foam, and therefore loading efficiencies will be computed and related to the overall degree of deformation that transpired in the foam. While Alderson and company has already studied the loading of glass beads into the matrix of auxetic foam, my task on hand is to look at how the foam deforms at a structural level, and how this could be related to the particle trapping efficiency of auxetic foam. This work is largely currently exploratory in nature for the meanwhile though, and as such, applications are still to follow. What is nice about auxetic materials though is that the deformation isn't really dependent on scale. That is, size doesn't truly matter, as the saying goes. Therefore, structural studies on auxetic foam may carry on to much smaller templates with which finer and finer particles can be subsumed into the system, until, maybe, perhaps, administering drugs into the bloodstream may already be carried out using fine auxetic transport systems.